Okay, and we're going to continue with stoichiometry now. All right, so I've put aside a couple of different questions that we're going to be looking at as a continuation of the previous lesson. I'm hoping that we'll manage to get through most of them and that I haven't done too much overlap. All right, so a lot of the stuff I've got put aside for today is going to be, I guess, a little bit of a different challenge. Okay, so there we go. I'm going to share my screen and we're going to get going. All right. So the first question that I've put out here, oh, sorry, just give me a second. My power cable has not been plugged in. Just quickly plug it in for me. Sorry. Whoopsie. The problem when you don't have things plugged in. There we go. Okay, quickly run it in. There we go. So the question asks, what mass of water is formed when hydrogen reacts with 6 grams of oxygen? Now, part of what makes this question particularly challenging is, thank you, is that I haven't given you a balanced equation. But I think most of you are smart enough, hopefully, that you know that hydrogen plus oxygen goes to give us water. Okay. So over here, we've got our starting materials on the left-hand side and our products on the right-hand side. We've also got, in order to work with this equation, we've got to do balancing of equations. And I haven't yet done balancing of equations, but it's important for you to do and to know how to do and to know how to bring in. So when we talk about balancing equations, what we're doing is we're effectively making sure that all of the atoms of the elements that we get in our starting materials side, we still have in our product side. This is because matter is conserved. Matter cannot be created or destroyed as far as we look when we're considering chemical reactions. If you go beyond chemical reactions, then by all means you can destroy matter, but we're not looking that far. It's not tested in the syllabus, so we stop. Okay. If I look on this side, I can see that I've got two hydrogens, diatomic, and I've got 2 oxygens. On this side, I've got 2 hydrogens, but I've only got 1 oxygen, so I must put a 2 in front of that. I put a 2 in front of water, I now have 4 hydrogens, and I now have 2 oxygens, so I've done a bit of balancing. And on this side, to make sure that it's balanced, I should put a 2 in front. Now that was just me quickly reminding you how to balance an equation. I would like to hope that by this stage, you all have definitely balanced an equation. The next thing that you got to remember is what this balancing means. It means that 2 moles of hydrogen will react with 1 mole, because there's a 1 there. So it will react with 1 mole of oxygen to produce 2 moles of water. Okay, so the important thing that you need to realize here is we're doing moles of hydrogen, moles of oxygen, so 2 to 1 to 2. This tells us the ratio in which they're going to be reacting with each other. Now what we've got to do is we've got to use the information that we were given. We were asked what mass of water, so under water I'm going to put question mark M. That tells me I'm looking for what mass of water is formed when hydrogen reacts with 6 grams of oxygen. Now because they didn't tell me how much hydrogen there was, I have to assume that it is excess. Excess means more of it than I need, okay? So if I've got more hydrogen than I need, then I don't have to worry about how much there is. So what I'm going to do here is I'm going to start by working out how many moles of oxygen I have. So I do this by saying that the number of moles of oxygen is equal to the sample mass over the molar mass. The molar mass of oxygen, if I look on my periodic table, and I've sent all of you a copy of the periodic table, oxygen has a mass of 16. It's diatomic, so there are 2 of them. So that gives us 32 grams per mole. So over here, I'm going to have 6 grams divided by 32 grams per mole. Tells me that my number of moles of oxygen is 0,1875 moles. I mentioned to you when we started this section on Monday that I don't like to round up in terms of moles. I don't like to change this to say, oh, it's 0.19, because it isn't. It's less than that. So I tend to prefer here to always make sure that I use the correct number of moles. Now what I've got to do is I've got to use the mole ratio. So I'm going to just work on the side here a little bit so that we can hopefully get all of this in. So I'm going to say 2 moles of hydrogen will react, 2 moles, I lie. We're not caring about hydrogen, we're caring about oxygen and water. We've got enough hydrogen, so I'm going to take that away. We have 1 mole of oxygen will react to produce 2 moles of water. So I don't have 1 mole of oxygen. I only have 0.1875 moles. But the ratio is 1 to 2. So the number of moles of water is going to be twice as many as the number of moles of oxygen. So because of that, I can say that I have 0.375 moles of water that are going to be formed. This assumes that there's no wastage, that there's no loss, that nothing disappears or gets taken away or doesn't happen. All right. So if we continue from here, I can say that the number of moles of water is 0.375. And then the question was, what is the mass? So I'm still going to use this equation that N is equal to little m over big M. The molar mass of water is the mass of hydrogen, which is 1, plus the mass of oxygen, which is 16. So it's 2 times 1 plus 16 gives me 18 grams per mole. And I'm not going to work backwards. I'm looking for the sample mass. So I prefer to rearrange and say sample mass is number of moles multiplied by molar mass. This is going to be my number of moles, which is my 0.375. My molar mass is the 18 grams per mole. And if I multiply those two together, I get that I'm going to get 6,75 grams of water if hydrogen reacts with 6 grams of oxygen, and that's the limiting amount of hydrogen that we get. All right, I'm going to quickly check in. You're going to have to speak up though, or message if you have any questions on this. I think the trickiest part of this was probably writing out the balanced equation, but you need to be able to write out a balanced equation if you're not given it. So you need to be ready to know what parts to put together, or if you're given an equation but it's not balanced, you need to know how to balance it. All right, so I'm going to quickly clear everything that we've got here, and I'm going to scroll down to the next question. The next question is a little bit more detailed. I know I'm ramping us up very slowly, but it's just that I don't want to overwhelm anyone too quickly and lose you completely. Okay, ma'am, when did you work out the mass of the water? Oh, sorry. The question was, when I work out the molar mass of something, I'm always going to ignore any stoichiometric coefficient, which is that number 945, because that isn't going to affect the mass of 1 mole of the substance. These numbers that we have in the front, we use to determine how many moles of, in this case, butane react with oxygen to produce how many moles of carbon dioxide and water vapor, but they do not affect our molar mass. So your molar mass doesn't depend on the number in front. I always use a very bad example, but with COVID-19, maybe it's an even worse example, where I have the same mass, whether I'm on my own or with 5 people, okay? My mass isn't going to go up because you need 5 of me to do a job, okay? So the mass of a substance, so mass of water, mass of whatever, doesn't depend on the number in front. However, when it comes to these small numbers behind, those are telling us 2 hydrogens to 1 oxygen. So those would affect our mass, but not the balancing numbers or the mole ratios or the stoichiometric coefficients in it. All right, let's quickly get into this question. It says butane will burn in excess oxygen. Once again, excess oxygen means we've got more oxygen than we need. And in real life, the way that we get excess oxygen is we'd be burning something in an open room. There's enough oxygen in the air that there's excess oxygen most time. The only time that you wouldn't have enough oxygen in the air and oxygen might be limiting is if you had closed all the windows, and then you hear those crazy stories of people suffocating because they lit a fire in a room and the fire burnt all the oxygen and they closed the windows and gone to sleep and they went into coma and died. Okay, crazy stories, but those kind of weird things happen when you've got a shortage of oxygen. So butane, which is this, will burn in excess oxygen according to the equation below. If 32 grams of butane burns, the first question is, what is the mass of carbon dioxide formed? So we are looking for the mass of carbon dioxide, but the only thing that we've got enough information about to work out is the butane. Because we've been given the mass of butane and we've been given its formula, or we know how to work it out, we can work out the mass using the equation we're going to have to work out the mass of this by working out the number of moles first. So the number of moles of butane is what we're going to be working out first, and that is going to be equal to the sample mass over the molar mass. Okay, so the number of moles of butane is equal to the sample mass, which is 32. The molar mass of butane, C4H10. You're going to have to go and look on your periodic table. I'm not going to keep flipping back to the image of the periodic table, but I did send out a link before we did the last lesson on all of the different platforms of a periodic table that you can quickly open. So if you look at carbon, you'll see that carbon has a mass of 12. And if you look up hydrogen, you'll see that hydrogen has a mass of 10. So if we do that, we've got 4 times 12 plus 10 gives me a mass of 58 grams per mole. Okay, so it's 32 divided by 58, which gives me an answer of 0.5517 moles. Now, if you look at your mole ratio, it's 1 butane will give me...
Ma'am?
Yes? Did I do something wrong already?
No, ma'am. I want to ask, is this thing balanced, the equation?
It should be. I haven't actually checked, but glancing at it just quickly, yes. Okay, so I've got 4 carbons on this side and 4 carbons on that side. 10 hydrogens there, 10 hydrogens there. Here we've got 18 oxygens. There we've got 8 oxygens and... Wait. Is it balanced?
Yeah, that's what I'm asking. It's not balanced, ma'am, because of the oxygens.
You're right, it isn't. I always assume that whenever I'm given an equation, it's already balanced. If you're given something and it's got numbers, it should be balanced. In this case, you're 100% right. It looks like we're short on oxygens. We get 18 oxygens there. I've got 8 oxygens there and 5 oxygens there. So I should actually only have 13. So somebody didn't do this right. It should be, 13. So this would be 6.5. Now, the good news about this is that it isn't actually going to impact my first answer. So I'm going to keep going from where I am because we're already assuming that oxygen is in way too much excess. But I will come back to that again when we do 2.2. It's a very rare case. I actually took this from another question paper, that you end up with something that's incorrectly balanced. Usually if there are no stoichiometric coefficients, you must check it. But in an exam, if they've incorrectly balanced it and you use those values, they cannot penalize you, just so you know. Okay. Miller's here as my checker. I've started to learn I never fight with him. If he raises an issue, there's a problem. Well done. All right. So we've worked out over here the number of moles of butane. Now we need to work out the number of moles of carbon dioxide, and it's going to be 4 times as much because this is a ratio of 1 parts to 4 parts. So the number of moles of carbon dioxide is going to be 4 times 0.5517. If you use a value which is 4 times as much, you don't actually have to do that calculation. So it's 0.5517 times by 4. Ideally, you do that without rounding it up, but isn't the end of the world if you do. So here I get 2,2068. It also doesn't matter if at any point you round anything up to 2 decimal places, it's still okay. So from there, what I'm going to need to do is I need to work out the mass of carbon dioxide. So I'm going to use the fact that number of moles is sample mass over molar mass. And I'm looking for the sample mass of carbon dioxide. Sorry, that's round bracket disappeared itself. And from this, I'm going to say that the sample mass is going to be the number of moles multiplied by the molar mass. The molar mass of carbon dioxide is going to be 12 from the carbon plus 2 times 16 from the oxygen, which gives me 44 grams per mole. And therefore, I'm going to have 2,2068 multiplied by 44, which gives me an answer of 97,10 grams. All right, so that is how you'd work out the mass of carbon dioxide which would be formed. Now, the important thing that I'm hoping you're beginning to get here is how the mole ratio idea is working. So what I did here was I first of all worked out the moles of butane, then I used the mole ratio, which are the big numbers in front, to link how many moles of butane react to produce how many moles of carbon dioxide, and then I worked out the mass of carbon dioxide. All right, I'm quickly going to clear this because I just want to balance this equation properly and make sure that we've got it done correctly. So if I have C4H10 plus 9O2 goes to give us 4 CO2. Yes, Tasneem?
Ma'am,
Yes.
since it's organic chemistry balanced equation in combustion,
Yes.
what is are we going to do that formula where you take the one side divided by the other side times 2?
There isn't an official formula. Not one that I use. I just know here that I must have the same number of carbons on both sides. I'm not quite certain which formula you're referring to. Sorry. So
Okay, thank you.
don't stress about it. If it works and it applies, that's fine. But I'm just quickly balancing this here, and I will eventually times everything by 2. So over here, that I've got 8, and then over here I ended up with 13, which would have given me, this should be 6.5. But the problem is you can't have a balancing number of 6.5. So the trick there is to get rid of it is you times everything by 2. So it actually changed to a ratio of 2 to 13 to 8 to 10. All right. Fortunately for the first one, because we assumed that we had an excess of oxygen, it didn't matter at all. Okay. The other thing that I need to just quickly remind myself of before I lose it on my calculator was how many moles I had. All right. So the thing that I'd worked out previously is that the number of moles, in fact, I can go back 2 steps, but the number of moles that I needed in order to react with everything else was 2,2068 moles. Okay, please, that isn't going to change anything. This then, if we divide by 4, this will still be 0,5517. Okay, so I like to record what my moles are somewhere on the sheet just that I can remember. Now the question asked what volume of oxygen reacts. So we're now going to go back and we're going to work out what volume of oxygen. Now remember here, oxygen is a gas. Okay, so when we deal with volume of oxygen, we're going to use the number of moles is V over Vm. Okay, so it's the volume of gas over the molar volume. So the first thing I need to do is work out how many moles of oxygen I have. So if this is a ratio of 2 to 13, I can say that we get a ratio of 2 to 13. The 2 part is 0,5517. So the 13 part, if I divide this by 2, now you've got to be careful here. I'm going to have 0.5517. I'm going to divide it by 2 and then times it by 13 to get the ratio. So I usually view it as divide by this number times by this number tells me my ratio gives me 3,5861 moles. Okay, there are other ways to convert from moles to another, but by taking this number of moles and dividing it by 2, I'm working out what 1 is in the mole ratio of 2 to 13 to 8 to 10. And therefore, because I've worked out what the 1 is, when I times it by 13, I get a number. Okay, so here I know that if I have all 32 grams of butane combusting, I will have that many moles of butane. And if that many moles of butane react, they will react with 3,5861 moles of oxygen. So to work out the volume, I can say that the volume is equal to the number of moles multiplied by the molar volume, which is going to be 3.5861. The molar volume here, we have to put in an assumption that it is at STP. If it isn't, you may be given a different value. So here we're going to times it by 22.4. And that will give us an answer that the volume is 80.33 decimeters cubed. All right, I hope that that makes sense to everybody. Quickly take a screenshot if you need to so that I can scroll down and continue. All right, cool. I'm going to quickly clear everything and then we can move downwards. All right. I'm going to start giving you a little bit of time to do some of the questions as well, because I think sometimes when you watch somebody else do everything and you don't do them as well, you don't really pay as much attention. So what I'm going to be doing here is as I go through each question, I'm going to give you a quick chance to do the work as well so that we can compare it and see what you've got. All right, we're only going to do one question at a time, so I'm not going to make you go too far ahead without any answers. So we are told that 10 grams of iron, I'm going to be nice, I'm going to give you the heads up as to what things are, otherwise this could be very fun. Iron is Fe, and it is burnt in chlorine. Please remember chlorine is diatomic to form iron 2 chloride. Sorry, iron 3. Iron 3 makes it Fe3 plus, chloride is Cl minus, and when we combine those two, we're just going to have FeCl3, okay? So I want everybody using the fact that it's iron and chlorine to form iron chloride to quickly write down a balanced chemical equation. I'm going to pause my sharing while I write it down and you can do the calculation as well, and then we can compare afterwards. Okay, I know I haven't given you very long, but I don't think you need too much longer than you've already had. All right, brilliant. Let's resume sharing. So what I did here was I started off with FeCl2 and FeCl3, and then I realized that if I've got 2 chlorines on the starting materials and 3 on the products, the lowest common multiple of those 2 would be 6. I needed to have 6 chlorines, so I put a 2 in front of the FeCl3, and to get 6, I put a 3 in front of the Cl2. So now my number of chlorines on both sides is 6. And then I realized that if I have 2 ions on the product side, I needed 2 ions on the starting material side. So that makes everything over there nice and balanced. All right. The next question asks for the number of moles of chlorine, which will react with the iron. So you have been given the number of moles, well, enough information to work out the number of moles of iron. Your question is to work out the number of moles of chlorine. All right. Once again, I'm going to give you a chance to do it first, and then I'm going to share my answer. Can I quickly, just before I go any further, can I just quickly check from people with thumbs up? Is this okay? Is everybody good with, do you like getting given an opportunity to try and answer it first? Okay, good. I think it keeps you on your toes. Otherwise, you're falling asleep while you watch me do it. Okay, so I'm going to pause, quickly do it. Go for it. The molar mass of iron is 56. I'll save you some time. All right. I've managed to finish that. Can I please ask as soon as you've finished it, if you can just give me a thumbs up so that I can see that we can move on. Okay, that's good. All right, so the answer that I got was I first of all worked out the number of moles of iron by taking the 10 grams of iron and dividing it by its own molar mass, which is 56 grams per mole, which gave me an answer of 0.1786. Then what I did was I said it's in a ratio of 2 to 3. So I took the number of moles here. Iron would be 0.1786. I divided it by 2 to get what 1 was, times it by the 3, and that gave me 0.2679. Please, if you rounded and you got 0.27, that is fine. Nobody's going to freak out. You got a minimum of 2 decimal places and you've got it there. All right. Then the next question asks us, what mass of iron chloride was formed? So you're going to use your mole ratio to get the number of moles of iron chloride, and then the molar mass to get the number of grams, okay, or the mass. So I'm going to pause sharing, and I'm going to give you a chance to quickly work out the next part again. All right, once again, if you've got the answer, please just quickly give me a thumbs up. Okay, good. So the answer that I got was 29,02 grams, because I worked out that this was a ratio of 2 to 2, which means that whatever number of moles I had for my iron, I'd have the same number of moles for my iron chloride. So this is also 0.1786. So it's a ratio of 1 to 1. Yes, it's 2 to 2, but 2 to 2 is 1 to 1. And that gave me the mass over there. All right. I hope everybody's okay with this. If you aren't, quickly speak up if there are any errors. Okay. And the last question here asks, how many atoms of iron reacted? Now, as soon as we're talking about atoms or molecules, we're talking about that particle formula. So we're going to be using the equation that the number of moles is the number of particles over Na, or you may write that the number of moles is equal to the number of particles over 6,02 times 10 to the 23. All right, so I'm going to quickly pause and I'm going to give you an opportunity to work out how many atoms of iron reacted. Please remember you must use the correct number of moles, which is the same as the number of moles of iron atoms that reacted. All right, once again, if you're done, quickly give me a thumbs up. Well done. Okay, fantastic. That's a large number of you. Okay, so I'm going to quickly show you my answer. So I said that the number of moles of iron was 0.1786, and we were going to use this formula. So I multiplied that value by that value, and I got an answer of 1,0. I guess you could round it to 1,08 times 10 to the 23 atoms of iron. Please be very careful. If that asked you, I guess it's not going to really change it, but if that asked you how many atoms were formed here in the product, you'd have to realize that your iron 3 chloride was actually made up of a total of 4 atoms. So sometimes we get technical, like I may have here that many moles of chlorine gas, but I have twice as many atoms if I'm now snipping the 2 chlorine atoms apart from each other and counting them individually. All right, so you can make the numbers change if you change what quantity you're looking at. All right, I'm going to clear all of the drawings. If everybody's good, quickly take a screenshot if you need one. Please, if there are any things that you need clarity on, ask right now. All right, so I'm going to do just one. Yes?
Ma'am, may you please just go back to that one? Yeah, I don't understand what you meant by the atoms of iron chloride.
Okay. So if I'd asked you how many molecules or formula units, sometimes people get really fussy there were, of iron chloride, because it's got the same number of moles here and here, I could say that my number of particles of FeCl3 would also be 1 times 10, let's just write this neatly, 1,075 times 10 to the 23. But that would be units or molecules. If they asked me over here how many atoms I had, I'd have to realize that iron 3 chloride, if there are this many packages or molecules, I'm going to call it a molecule even though it's ionic, okay? So if I have iron 3 chloride, it's made up of Fe and 3 Cls, okay? If I were now to tell you, let's just use a simple example. If I told you that there were 12 of these, how many ions would there be? There'd be 12 ions, and there'd be 36 chlorines, agreed? If there were 12 of those. So you've got to be careful that when we work out the number of particles, what type of particle we're referring to. So here, the number of particles that are iron 3 chloride would be that many. But since each of those, if I were to remove all of these bonds, can be turned into 4 separate things, 1, 2, 3, 4, I could actually end up with more moles that are smaller in quantity because they're atoms instead of molecules. Don't panic too much about it. It's me expanding on a question that wasn't asked. All right.
Okay, ma'am. Thank you.
Pleasure. So I was just explaining that it wouldn't always work that way, or there might be sneaky ways that they could make it not work normally. All right. The next thing that I want to just quickly chat to you about before we move on to limiting and excess reagents is waters of crystallization. Now, I've included 2 examples here that have got waters of crystallization. So basically, it's water that gets trapped in the crystalline structure of usually an ionic substance when it is crystallizing. So as it's forming crystal lattice, water molecules get trapped in that crystal lattice, and the water molecules conveniently, because they're positive and negative charges, actually form part of the lattice in a very, very predictable way. So we know, for example, that when copper sulfate, there's an example, when copper sulfate forms a crystal, and it's the pretty blue crystal that's pretty much the same color as the pen I'm writing with, it will always trap 5 water molecules to every 1 copper sulfate when it forms its crystal. When sodium carbonate does the same thing, it'll trap 10 water molecules to every 1 sodium carbonate. When that little thing over there shouldn't be there, let me just quickly erase it. Okay, so when zinc chloride forms its water crystal, it'll trap 4 waters. So you need to know that these .5H2Os are important because they're trapped water that's trapped inside the molecule. You should have covered water crystallization somewhere around about grade 10. And I know what I do with my students is I take copper sulfate that's hydrated. As soon as it's got water as part of it, it's called hydrated. And then we put it in a test tube. So we'll have our test tube here, and at the bottom of it, we've got the beautiful copper sulfate crystals. And then what we do is we stick it in a flame. So we stick it under a Bunsen burner, and it burns. Well, it doesn't really burn, but it's on a Bunsen burner. And what happens very quickly is that all of the blue stuff goes kind of paler in color until it's kind of a whitish gray. And what I've done here is I've actually boiled off all the water, and I'm left with just CuSO4, which is white. So this here is blue in color, and this here becomes white. And we call the copper sulfate that's got the waters of crystallization hydrated, and when we remove them, we call it anhydrous. We don't call it dehydrated. That's kind of fun. But at a metric level, they're not so likely to bring in this concept. It's just that if you ever see it, because sometimes if we're 100% honest and we're dealing with oxalic acid is a crystal. And oxalic acid has waters of crystallization that you shouldn't ignore. All right. So the question here that I brought in says, determine the concentration of a copper sulfate solution formed when 20 grams of hydrated copper sulfate are dissolved in water to make up a 1.8 decimeter cubed solution. Now, what we've got to know that's very important is that this whole formula determines our molar mass. So we've got to include the mass of the waters that we're weighing because they exist and they're there. We can't ignore them. We can't wish them away. So what we would do here to solve this, and this isn't going to be one where I abandon you and say, good luck, do it on your own. I'm going to quickly run through how to do it. So the first thing that I need to do is I need to work out how many moles I have of copper sulfate. Okay, and it's copper sulfate with the waters of crystallization in it. So the molar mass of copper sulfate is going to be copper, and you're going to have to double check me on this, but I think it's 63.5. Sulfur is 32. Oxygen is 16, and there are 4 of them. Plus the 5 times the 2, there are 10 hydrogens. And there are 5 times the 1 is 5 times 16 for the oxygens. You are welcome if you wish to treat water as having a mass of 18 and then multiply things out. It's entirely up to you. So here I'm going to have 63.5 plus 32 plus 16 times 4 plus 10 plus 5 times 16, which gives me an answer of 249.5 grams per mole. All right. From there, I need to work out the number of moles being sample mass over the molar mass. So the number of moles is going to be my sample mass of 20 grams divided by my molar mass of 249.5. So if I have 20 and I divide it by 249.5, I get an answer of 0.08 moles. All right, so that tells us how many moles of copper sulfate we have. But because it tells us how many moles of the copper sulfate and the water we have, once we put it in solution, we only actually care about the copper sulfate. So the question asked us determine the concentration. I can say that C is equal to N over V. If there were 0.08 moles of all of this, that means there's also 0.08 moles of just this. So our number of moles of anhydrous copper sulfate, or just the CuSO4, will be 0.08. The volume here was 1.8 decimeters cubed. And if we divide this, or those two values by each other, we end up getting to an answer for concentration of 0.0445. So I'm going to call it 0.045 moles per decimeter cubed. The only reason that I put this particular question in is that I feel that it's very important that when we look particularly at stoichiometry in general, that at least a mention is made of waters of crystallization. All right. It's not likely to be a big focus in your exams, but if it ever does pop up, I don't want you to be completely oblivious as to what it is or how it works. All right. Ladies and gentlemen, does that bit make sense to everybody? Okay. I'm going to quickly clear this and stop sharing for just a second. We're almost halfway through our time. So what I'm going to suggest you all just quickly do is to stand up, stretch your arms and legs. We're not normally going to have this many sessions in a week. It's been a little bit crazy for this week. And I want you to just quickly stretch, and then we're going to continue with some of the trickier questions going forward. Okay, so quickly just stand up and have a bit of a stretch. All right, and let's continue. Okay. Whew. So let's carry on from here. There's a question. Could I bring that slide back? I don't think so. I'm really sorry. Unfortunately, once I close my sharing, because I'm not sharing a whiteboard. If I share a whiteboard, it keeps my whiteboard. If I'm sharing my screen and I stop sharing it, it disappears. But I'm pretty certain that someone will have taken a photo of it, and I'm sure that they'll share it on the groups just now. All right. Otherwise, it will be in the video recording of this. I'm really sorry. Sometimes it happens. All right. Okay, please next time when we get to that point, just quickly ask, because unfortunately I can't always go back. There we go. See, Tasneem's got it. Sorted. Yeah, I've just got to make sure you and Tasneem are in the same group, because unfortunately we've got too many people for just one group. So you guys are split between two groups. All right. So here we go. We're dealing with our first question that deals with limiting and excess reagents. And I am going to struggle just quickly to get this on a page so that I don't have tons of space around it. Okay, I'm going to try a quick trick here. Just give me a second. This is one of my favorite tricks, to quickly be able to take a screenshot of just the bit I want when it doesn't let me do it. All right, there we go. All right, so we're in a situation now where we're dealing with limiting and excess reagents. Now, just quickly before we go there, that should be an arrow, and I want to chat to you about what the idea of limiting and excess reagents mean. I'm sure that through the lockdown, many of you have actually experienced limiting and excess reagents in action. It's what happens when my children go and they decide they're going to bake a cake, and they've weighed out the flour and the sugar, and they put it all in the bowl, and then they look up and they go, "Mom, we've only got one egg." And suddenly our cake goes from being a cake to not being a cake at all, because we could only have made half a cake if we needed two eggs to make the cake. So when we deal with limiting and excess reagents, it's if you're short of one of the things, you're only going to be able to make less products. Okay, so that's kind of the limiting reagent in our household tends to be either sugar or eggs. They get run out of first. So limiting reagent is the substance which limits the amount of product that can be made. Excess reagents, you have more of it than you need. And unfortunately, just like in baking, if I don't have the eggs, it doesn't matter how much flour and sugar and all of the other ingredients I have, I can't make more cakes. So having tons of excess reagent on its own isn't going to solve the problem. And usually we work out which of these is limiting, because the limiting reagent is what determines the amount of every one of the products that we get. All right. So I always find that when I deal with an equation with limiting and excess reagents, I start by rewriting the formula. I know a lot of people don't rewrite the formula, but I find that it's a good way for me to be able to write additional information that I want on it. And sometimes there isn't actually enough space. Now, this particular reaction that they're choosing here is the reaction of sodium thiosulfate with hydrochloric acid. This is a reaction that the matrix should know because it's one of the reactions that we can give you when it comes to rates of reaction. When sodium thiosulfate reacts with hydrochloric acid, it forms sulfur, and that makes the solution go cloudy. So you cannot see the bottom of the container. So we quite often do the reaction, this particular reaction, on top of an insert or something with a cross on the bottom, and we actually time how long it takes for the sulfur to make the solution so cloudy that you can't see through it anymore. So matrix, this is an equation you should have seen before, or if you haven't yet done rates of reaction, you hopefully will see soon. So we are told that 345 grams of sodium thiosulfate is reacted with 170 grams of hydrochloric acid. Now, just for the record, hydrochloric acid normally wouldn't be given by mass if it's aqueous. There's a kind of contradiction there, but we're going to assume here that when we say it's aqueous, it's 100% HCl, and the water that makes it aqueous has no mass, because otherwise we've got a problem. All right, so the first question here is to determine which of the reagents is the limiting reagent. Now, in order to do that, you need to work out the number of moles of each of these. Both of them have been done in masses, so we're going to use the equation N is equal to little m over big M. I'm going to quickly pause because I think all of you should be able to work out the number of moles of both of those, and I'm going to quickly ask you to work both of those out for me. All right, I'm going to be doing the same behind the scenes, and then we'll compare. This is where it's really useful to remind yourself what things are by putting their formulas in brackets. All right, I've managed to get both of the number of moles. Can I quickly ask anyone, or when you get there, that you just quickly give me a thumbs up so that I can keep track of where people are? Okay, I think we're almost halfway, so I'm just going to give you a tiny bit longer. Unfortunately, my writing is all over the place. I am apologizing, but I'm pretty sure you'll cope with it. All right, so that was it. So if I look here, I get that the number of moles of sodium thiosulfate is 2.18 moles, and the number of moles of hydrochloric acid was 4.66 moles. Does anyone disagree? So I've got my molar masses worked out down the side here. Okay, and then I've followed through with my formulas over there. Okay, so we need to know which one here is the limiting reagent, which means we need to look at their mole ratios and determine which one we have more of. So I'm actually going to remove my calculations here to get their molar masses. I did them, their use has passed, and I'm now going to use limiting and excess. So what I always do, and different schools probably have different approaches, but I think most teachers, when it comes down to it, do the same thing, is that I know that my ratio here, if I look at the formula, is 1 sodium thiosulfate to 2 HCl's. So I pick either one of these. I don't mind which, it doesn't matter. I say, right, this is official, this is the number. So if this is 2,18, my question is, how much HCl will I need to be able to react with all of it? So I go 2.18, I divide it by 1 to get what 1 is in the ratio. I times it by 2 to get what 2 parts is in the ratio, and I get that it will react with 4.36 moles. So that means that if all of this reacts, I need 4.36 moles. Then I go and look, do I have 4.36 moles? And if the answer is yes, then this is in excess. We have more of it than we need. If we have more of it than we need, then the other substance must be the limiting reagent. It is the thing that will determine how much product we get. Wait, yes, because we have more of our HCl than we need. You could have chosen to do this the other way around. So let's pretend that I didn't go and put in, oh, I want to leave those there, just erase. Let's pretend that I didn't choose to put in the sodium thiosulfate. I instead put in the HCl as 4.66. And then I said, all right, cool. So all 4.66 reacts. I divide it by 2 here to get what 1 is. I times it by 1, and I discover that I would need 2.33 moles to react it with. Then I go across here and I look and I see, wait, I don't have the 2.33 moles that I need. Therefore, it's a limiting reagent. You do not need to do both of those 2 steps. Either one of them will work. Okay, in fact, I'm just quickly going to go back to that one, because at least then I've got a calculation that shows why it was. So the answer here, once you've got through all of that, is you've got to actually go and do this kind of story sum answer. Which one of the reactants is the limiting reagent? My answer is sodium thiosulfate. Please, you've got to do all of the working out to get there. And usually your mark allocation would be 1 for each number of moles, 1 for kind of doing something to determine which one was the limiting, and then 1 for the answer. Okay, so at this point, what I'm going to do is I'm now going to go and assume that instead of working with these masses, which could be wrong, I'm going to work with the limiting reagent of moles. So the only number that I keep from all of those is I'm going to say this 2,18 is important. This 4,66 we know was more than we need, so putting it in is going to make us unnecessarily confused with other answers. Okay, so that is the only thing that I need to keep from the work that I've done up till now in order to answer the rest of the questions. Okay, so that over there is how many moles we have. Then the question says, oh, damn. No, it isn't the only thing we need to do. I need to totally undo all of that working out because the question then asks for the mass of the reactant in excess. Oops. So we need to work out how much too much we have. Sorry, I've got to undo this individually. So I worked out, sorry. I hate it when I undo things. I should have just done clear all and then I wouldn't have an issue. All right, I don't have to go too far back. There we go. Okay. So the question was here, how much too much do I have in excess? So I'm just quickly going to work it. I apologize. You probably got all of yours written down, but mine's all in my head. So over here, if I'd said we had 2,18, 2.18 times 2 means that I would have 4,36. So the amount of moles I need to work out effectively is I know that the number of moles of HCl that I have in excess is going to be the 4.66 minus the 4.36. Okay, there we go. That's what I needed to get from there. So 4.66 minus 4.36. You're all lucky that you actually write on paper. So once you've written things down, they don't disappear. Okay, now I can go and get rid of all of that writing that I just deleted and had to put back so that I could see it. All right. So the question here asked me calculate the mass of the reagent in excess. So I assume when they say the mass of the reagent in excess, they're asking how much too much do I have of what I'm looking for. So they don't want to know the mass of hydrochloric acid. They want to know the mass of hydrochloric acid that isn't going to react. I've just worked out that I've got 4.66 moles and I only use 4.36 moles. So 0.3 moles don't react. So the number of moles is sample mass over molar mass. And the sample mass will be N times molar mass. So 0.3 moles multiplied by the mass of HCl, which is 36.5. That gives me an answer that I have got 10,95 grams more than I need. So this answer here is 10,95 grams. All right, apologies, I haven't done this question before, which is why I was deleting things that I later, or erasing things that I later would need. All right, so jumping back to where I was going with the rest of this, I know here that this was only 4.36 moles that reacted. All right, is everybody happy up until the end of 5.2? If you're not, please quickly speak up, and then I'll quickly go through your question. Otherwise, I'm going to continue with the rest of the questions. Okay, I presume that means everybody's on track. I will check in with you properly at the end of this question. The question then says, calculate the maximum mass of sulfur that can be produced in this reaction. So they want to know what is the mass of sulfur that we can produce. Please note here, this is going to be the number that you use. You may use this one if you wish, because it's not the 4.66, it's the number that I used. Can I ask everybody to please try and calculate the mass of sulfur? I'm going to quickly pause sharing. So I'm going to give you a chance to work it out as well, so that you stay on your toes and you stay involved in the process. All right, go for it. Okay, when you're done, give me a thumbs up. Okay. Okay, so what I got here was I got 69.76 grams, because what I did was I worked on the mole ratio, which said 1 mole of sodium thiosulfate gives us 1 mole of sulfur. Therefore, both of them are going to be 2.18 moles. The molar mass of sulfur is 32 grams per mole, and I multiplied the values to give me 69.76 grams. You'll notice as we go through the questions, I have a habit of writing in the answers on the questions here. But you must also show all of your working out. It's just that because I've got a limited screen space, instead of a page where I can keep going down, I write them down there just in case I need them for another question later. All right. The last thing here is that they say it was found that when the reaction was completed, only 32 grams of sulfur was obtained, 52 grams of sulfur was obtained. Calculate the percentage yield. Now, we have not done percentage yield before, so this is a good time to bring it in. You'll notice that a lot of the questions are kind of bringing in new ideas and reinforcing ideas. So when we work out percentage yield, in very few chemical reactions do you actually get 100% of what you expect to get out. I know it sounds a bit crazy, but I guess on a very weird scale, you could compare it to a recipe that says this recipe will make 24 muffins, and you make it and your muffins are too big or too small or different, or some of the batter drops on the floor, you don't always get the yield. Okay, it's quickly answering a question. How come we don't consider the sulfur formed in the form of sulfur dioxide? Okay, please note the reason we don't consider the sulfur in the form of sulfur dioxide is that they're different. If they wanted sulfur dioxide, they'd have asked for it. So I understand what you're saying is that there is technically sulfur in the sulfur dioxide, but when we talk about massive sulfur, they're referring to the pure sulfur. Okay, it's just we don't get that technical about the mass of sulfur in where it is. If we say the mass of hydrogen, we mean H2. We don't mean hydrogen in water and in HCl and anywhere else. So it's just one of those terminology things that if you've been doing it for long enough, you'll know you don't split things up. There you say sulfur, you're looking for the thing that's sulfur, and over here, that one is your sulfur. Okay. All right, so the percentage yield that I got distracted from, I mentioned that it isn't always what you expect to get. Even in an industrial reaction, I know years ago I worked in a pharmaceutical company where one of the things that we did was we took a whole bunch of powders, weighed them out, stuck them in a giant vat, spun them around for about an hour for them to mix up, and then took them out again. 3 tons. You would think that you put in 3 tons, you get out 3 tons. Every time we lost roughly 3 kilograms of powder that just went into the air. So we'd have a yield of 99.9 something, but we never get 100% yield because some of the stuff, some of your sulfur might remain dissolved in the solution. Some of it might have fallen out the container. We obviously don't aim to lose it, but a percentage yield is usually, if it's above 100%, there's a problem. You made more than you could. Okay, so either it means that when you're weighing the mass of sulfur, it's not sulfur, it's sulfur and something else, or it's sulfur that's weight, so it's still got water in it. So usually a percentage yield cannot be bigger than 100. But your percentage yield is always going to be your actual yield over your theoretical or expected yield. What you really get over what you planned to get. So, and then times by 100. Percentage is always times by 100. So the actual yield was we only really got 52 grams. The amount that our calculations told us we should get is 69.76 grams. And if we times that by 100, we'll have 52 divided by 69.76 times 100 gives me an answer of 74.54%. Okay, and what's a little bit scary is in some reactions, 70% is a fantastic yield and everyone is very proud of themselves when they get them. Sometimes some reactions just don't happen and a 30% yield makes some people very happy. All right, so the amount of yield isn't necessarily an indication of a bad reaction, it's just something that you need to do. Do we always use the mass to calculate percentage yield? No, we could actually have done this from moles to moles. So if I use the number of moles here, and I work this 52 grams out into the number of moles, I could do the number of moles that I got out of the number of moles that I expected. So the reason I've chosen instead of saying actual mass over theoretical mass is it could be actual moles over theoretical moles, actual volume over theoretical volume, actual concentration over theoretical concentration. As long as we're dividing an actual value that we got over the theoretical value for the same quantity that we'd expected to get. All right, so it should always be a ratio of those two things in that particular way. All right, does this make sense to everybody? Okay, quickly take your screenshots because I am gonna at this point clear again. All right, so what I like particularly about this question is that it brought in limiting and excess reagents as well as percentage yields, which were things that we needed to. We haven't yet really hit the very, very tricky things, but I think it's important for us to establish decent foundations first. Because if you don't have the foundations, then me throwing hard questions just loses people and they can't really cope with it. All right, so we're going to carry on with another question. I've got a bunch of questions that a kind teacher was nice enough to donate to me because I find that I run out of questions and I know that most of my students have already done certain questions. So I'm trying to do different questions. All right, here's an interesting one. It's not impossible, It's nice, but it's one that you might struggle with in a test if you hadn't done it before. All right, so I'm going to quickly go and find you guys. There we are. Share the screen with you again. All right. So this question is dealing with concentrations and then with ratios of concentrations. So it says 10 grams of KMnO4. KMnO4 is potassium permanganate. Please get used to the different names of what things are. I find that it's important every time I see a formula to give a word to it, because some of you don't always know them, and it's nice for you to slowly but surely get used to them. So that many grams of potassium permanganate is dissolved in 250 centimeters cubed of water. You're asked to calculate the concentration of the water. We have done one similar to this before. You're going to be using the equation C is equal to N over V, coupled with the equation N is equal to little m over big M. All right, so I'm going to ask everyone, this is only, it's a quick thing, it's 4 marks, which is very generous. I'm going to pause share and I'm going to give you a quick chance to be able to do that. The hard question's actually the second part. Some of you are good at it and some of you just get lost. All right, so quickly work out the concentration. Just in case anyone is completely lost, potassium is 39, manganese is 55. And oxygen is 16. That one you might know though. Okay, I'm hoping that you've all got the right answer. Can I just quickly scroll through and ask anyone who's got the answer already, quickly thumbs up? Okay, good. Okay, brilliant. So I'm going to quickly share my screen and hope that I haven't messed up anywhere. I know I did this one, I messed up on this one in the last one, but I don't quite know why. I think it was that we were working out volume. So what I did here was I had my 10 grams, I divided by 158 grams per mole, and that gave me 0.06329 moles. I didn't round up. I then took that and I divided it by the 250 centimeters cubed of water. Please don't forget to make this 0.25 decimeters cubed. If you forget that conversion, things go very pear-shaped. And I got an answer of 0.2531, but we're just going to call it 0.25 going forward because it's easier. Then the question asks, how much more water should be added to 200 centimeters cubed of this solution. So we're only adding water to a small portion of this. So if we made 250 centimeters cubed of this, we're only going to take a little bit of it out and put it into another container, but it's only going to be 200 centimeters cubed. And they want to know how much more water must I add on top of this in order to change the concentration from 0.25 moles per decimeter cubed to 0.1 moles per decimeter cubed. Now, I don't know if any of you already know how to do this solution, to do a question like this. I'm going to ask again in a second. I'm just quickly going to, okay, I'm just writing that bit down because I think we've got everything else we need here already. So I'm just going to quickly take a snapshot of anything you need before I remove my writing at the bottom here. Okay, and it's gone. All right, so I'm going to quickly, I'm not going to stop sharing. I'm just going to open my screen so I can now see all of you, even if you can't see each other. I want to quickly ask with the thumbs up, who thinks they know what to do? Who thinks that if I said to you, go do it, they'd know how to do it? Okay, I can see one person. 2, 3, 4. Wait. Okay, 6 of you. Looks like about 6 of you know how to do it, which means that in the interest of assisting you, I'm going to give you some guidelines as to how to do it. All right. So the first thing that I would do personally is I would work out in the 200 centimeters cubed that had a concentration of 0.25 moles per decimeter cubed. I would work out how many moles I had. Because that number of moles, if it starts in here, will still be in the total container, even if we top it up with water. The water isn't going to add any more moles of potassium permanganate. Okay, so I would start by working out how many moles I had in the 200 centimeters cubed when we worked out the concentration in the previous question. Once you've got the number of moles of KMnO4, you're going to use the equation C is equal to N over V. You know that the concentration that you're aiming for is 0.1. You know the number of moles from what you did here, and you're going to work out what the total volume will be. But remember that this total volume is 200 plus the volume that you add. The question didn't ask us what's the total volume here. They asked us how much water must we add. All right. So this is what you're trying to work out. So what I'm going to suggest, if you don't know where to start, is follow my steps. Work out the moles of potassium permanganate in the sample of the potassium permanganate that you take out. Then, using the concentration that you're trying to get to and the number of moles that you will have worked out, work out the total volume that this needs to have, and then subtract 200 from it to work out exactly how much you had to add. I'm going to pause sharing now, and I'm going to leave what I've written on the board, on my board as well, and then I'm going to work out the answer. Please, can I suggest all of you do the same? Please be careful with your maths. I know I nearly did the same mistake again. I better not do it tonight. All right, I've managed to get to my answer. I'm just going to quickly ask anyone who's already managed to get to their answers. Thumbs up. Okay, well done. Okay, good. All right, fantastic. So the answer that I got, and I'm hoping it's right now, was 300 centimeters cubed. So what I did was when I worked with the concentration of 0.25, please, you may have left all the values on there and then your answer would be slightly different. That's fine. So I did 0.25. Please note that 200 centimeters cubed must be put in as 0.2 decimeters cubed. Think about your formula. It's number of moles over volume in decimeters cubed. So the number of moles that I got was 0.05. From there, I took that and I said, well, the new concentration must be 1 mole per decimeter cubed. I have got 0.05 moles. What total volume must I have? So if I then work that around, I rearranged it here so that I didn't do a spectacular maths mistake again, and I got 0.5 decimeters cubed. Please remember that that is the same as 500 centimeters cubed. If the total volume had to be 500, and we started off with it being 200, we must have added in 300 centimeters cubed to change the concentration. Technically, when we talk about reduce the concentration, we're talking about dilution. Some people can sometimes even do this using a ratio. So for example, you say, well, from here to here, it is in a ratio. If you look at it where this is, if we imagine there being fifths of a total, this would end up being 2.5 times, I guess, as big as the 0.1. You can kind of work with different manipulation ratios if you want to. But I strongly suggest instead of doing ratios, you convert to moles. You say, how many moles have I got and what new big volume, and you work out that way. So the other way that you can do this, and I'm just quickly going to ask you to take a screenshot if you need, because I'm going to clear. There is another formula that assumes that if you are only adding water and the number of moles stay the same, if the number of moles initial equals the number of moles final, and we can say that C is equal to N over V, then we can say that N is equal to C times V. So we can say C1V1 is equal to C2V2. I'm only showing you this afterwards because I want you to do the good maths. But here, if this was 0.25 times by 200, it will equal 0.1 times by V2. That should give you, if I haven't messed up here, that V2 is equal to 500. You don't even have to convert here because it's a ratio. So as long as these two volumes are both in the same unit, you're not technically working out the number of moles. Okay, so then we could get that this is 500 centimeters cubed. You could say, well, we started with 200, we ended up with 500. Therefore, the volume added is 300. This is a shortcut for people that like shortcuts, but you've got to be confident of your knowledge, and you've got to be sure that you're not adding in moles of your potassium permanganate anywhere else. It's not actually increasing the number of moles. All right, ladies and gentlemen, we've only got another 10 minutes left, so please don't leave. I just want to quickly do one last example with you. I'm going to stop sharing. I'm quickly going to find it, and then I'm going to capture it before we go onwards. We haven't done any really challenging questions up till now, but these are the kind of things that I want us to get used to doing, because they're very important going into your matric exam. All right, there we go. This is a nice one. Okay, let's go share with you. Okay, sorry, I've just seen that there's a chat. All right, so someone said work with ratios. Okay. You can work with ratios, you just got to be very careful because you may not get it right. Okay, that was not the share I wanted to share. This is the one I wanted to share. So hopefully everybody's seeing my nice, pretty, neat screen, because it's much easier to work on this one than the one with all the other writing. So silver nitrate reacts with iron 3 chloride. Please, just something that's very important about silver nitrate, and you're going to find I mention it a lot. It is the only soluble Ag plus solution or salt. So the only time that you're ever going to get silver ions staying in solution is if they're in silver nitrate. It reacts with our iron chloride to produce silver chloride and iron 3 nitrate. In an experiment, 25 grams of silver nitrate was mixed with 45 grams of iron chloride. First question is to balance the equation. Now this question here is a nice challenging one to end on. So I'm going to quickly give you just a quick chance to balance the equation yourself first. Okay, so I'm going to pause it. Can everybody quickly balance the equation? Okay. All right. Has everybody got a balanced equation? In order to balance the equation, you had to put a 3 in front of the silver nitrate and a 3 in front of the silver chloride. That is because there are 3 chloride ions there and only 1 there, so that had to become 3. And then as soon as your silver changed, so did that silver. We've got 3 nitrates and 3 nitrates, 1 iron and 1 iron. Please note we normally don't balance according to like nitrates. Like I don't go, oh, I got nitrates and nitrates. I should break it up into nitrogen and oxygen. But in this case, they're the only things that are made from nitrogen and oxygen, so you can cheat. Now you are asked to calculate the percentage yield of silver chloride if the actual yield is 15 grams. So what they are effectively asking us to do is what mass of silver chloride do we get? Because that will be our theoretical yield, and then to use it to work out the percentage yield. All right. Can I please ask everybody, I'm going to pause sharing just now, and I'm going to ask you, I know it's a big challenge right now, but we've still got another 6 minutes. I want you to see if you can quickly work that one out. All right. So I'm going to pause it. Just in case anybody doesn't know the values, I'm going to quickly look up silver. We need silver and chlorine. I think silver is 80 grams per mole, but I've actually got to check. No, silver's 108. There we go. Silver's 108. This is the long one. This may take us till the end of this lesson. All right, I apologize. Please note, I've just realized as I got to the end, this is a limiting and excess reagent question. I only worked out the one, so I'm going to have to quickly go back because I suddenly realized they'd given us iron chloride as well. Whew. All right, I finally got there. Can I quickly have a show of hands who thinks they've got to the right answer? Okay, cool. It's a good start. All right. Okay. Because I know that time is of the essence and we're nearly at the end, I want to ask who got an answer. Actually, tell me what your answer was. I'll give you a hint. I got an answer that was above 71 and below 72. Did everybody else get an answer that was similar? Okay, let's hope. I'm going to share. Let's quickly see what answers I've got here. 71,08. Okay, I got 71. Mine rounded up to 71,10. That may just be rounding. Okay. Oh, wow. You guys all got exactly 71,08. Okay, cool. Maybe I rounded at some point. So just to quickly give you an idea, and I hope that this is correct here. Yeah, okay. Someone else got similar to me. The good news is it looks like all of us would round to a similar number. So just quickly checking, you should have worked out the number of moles of both your silver nitrate and of your iron chloride. You should then have worked out that your silver nitrate was the limiting reagent and your iron chloride was in excess. All of these values here, just for the record, that's all my molar masses. Once I got the number of moles of silver nitrate, I worked out the number of moles of silver chloride, and I used that to work out the mass of silver chloride. I worked out that I should have got 21,09 grams, and instead of getting 21,09 grams, I got 15. So 15 out of 21,09 gave me an answer of 71,10. All right, ladies and gentlemen, we're already at the end of this lesson. At the end of your last lesson, I actually gave you a challenge where I asked people to answer a question and to get back to me with the answer. It was really nice to see who engaged and did it. There were actually a surprisingly large number of people who remembered. So my challenge to you at the end of this lesson is to please go and calculate the mass of the reactant in excess on completion of the reaction. So I effectively want to know, we've just worked out that iron chloride, there was too much of it. I now want to know what mass of it was there too much of it by. So how much of it did we have that was too much of it? All right, before I say goodbye to you, because I just quickly need to, I'm going to quickly take a screenshot of this so that, oh damn, that was my screenshot. Oops. All right, I'm going to quickly take a screenshot if I can of my screenshot. I don't think it's going to work very well. Okay, we'll leave it there. So I'm going to stop sharing now. I'm going to stop recording.